Good afternoon, everybody. Welcome to the second lab of Chemistry 112. What I wanted to do today is we are doing the second lab, which is the separation of a mixtures lab. When we start talking about mixtures, we'll talk about mixtures that are heterogeneous mixtures. Those are mixtures that are not the same consistency throughout. Or we also have homogeneous mixtures. Homogeneous mixtures are mixtures. Later we'll also refer to those mixtures as solutions. Homogeneous mixtures, homogeneous mixtures are ones that have the same consistency throughout. It's impossible to distinguish the different components that make up that mixture. And so the mixture that we're going to be working with today is a heterogeneous mixture. So it's a mixture that's made up of three different compounds. One of those compounds being ammonium chloride, the second compound being silicon dioxide or ordinary sand, and then the last compound is sodium chloride, NaCl. So what we're going to do is we're going to take those three compounds that are all present in this mixture, and we're going to take a sample of this, and then we're going to separate it out. We're going to separate each of those individual components out of that mixture one at a time. And then when we're all done, we're going to figure out what percentage of this mixture was ammonium chloride, what percentage of it was sand, what percentage of it was sodium chloride. And we're just going to look and see what percentages we get to see how that compares to what we know the actual values are. You're not going to be graded on how close you get to the actual value. Actually, you're not going to be graded on how close I get to the actual value, because I'm the one that's actually doing the separation today. So that makes it, there's a little more pressure on me that I have to make sure that I get a good score on this one. So the first thing that I'm going to do, if we read through the lab and we read through the procedures, these different compounds in there, each of them have different chemical and physical properties that allow us to separate them from each other one at a time. The first property, ammonium chloride, sublimes when we heat it up. Subliming is when a substance goes from the solid state right to the gas state. It doesn't melt. It just goes from a solid right to a gas. So we're going to take our sample, we're going to heat it up, and we're going to sublime off the ammonium chloride. And then when we see how much mass was lost in that process, that's going to tell us how much mass the ammonium chloride was. Then we're going to be left with a mixture that's the sodium chloride and the silicon dioxide. And to separate those two components, we know that salt dissolves in water, but sand doesn't dissolve in water. So we're going to add water to that mixture. We're going to stir it up, and then we're going to pour off the water with the dissolved salt in it. Then we're going to end up with two different evaporating dishes, two different dishes. One that has the sand in it that's now wet, and then the second one that has the water with the dissolved salt in it. Those two dishes, we're going to heat both of them up. The one will evaporate off all the water. We'll end up with dry sand, and we'll be able to weigh that, figure out the mass of the sand that was in that mixture. The second dish that has our salt water in it, we're going to evaporate off all the water, and we'll be left with the dry salt. And again, we'll be able to weigh that. So by separating each of those components one at a time based on their different physical and chemical properties, we'll be able to figure out the masses of each of those. So the first step is going to be to take our weighing dish, our evaporating dish, and weigh out approximately 2 grams of the sample to see how much we start with. So I will see you in a bit. We're back here at our friend the balance, and the first thing that I'm going to do is weigh out this evaporating dish, right? So this is an evaporating dish. It's a ceramic dish. You can see it's kind of tapered, and what it does is it increases the surface area of something, so that if you're trying to evaporate something, you've got a greater surface area so that it evaporates much quicker. What's interesting about these is if you turn them over and you look at the bottom of it, you can see there it says Coors Tech. And Coors Tech, well, that's the same company that ends up making Coors beer in Golden, Colorado. During the Prohibition era, they were no longer able to make beer, and so they actually started making laboratory-grade ceramics. And they spun that business off of the breweries so that they would be able to still continue to generate income. So we use them because they're pretty durable, they can withstand pretty high temperatures, and they don't break very easily. So what we're going to do is we're going to weigh this empty dish. And so in our lab experiment here we've got a report sheet that we've got unknown number 2. At least that's what it says on the label. And so when we get done and we get our final results, we'll be able to compare those results to what the actual known values are. So we're going to start here, and we're going to figure out what the mass of the empty dish is, and then we're going to add some sample and measure that, and then if we subtract the mass of the empty dish from the mass of the dish plus the sample, that will give us the mass of the sample. Okay, so that's where we'll go. So the mass of the dish with the sample in it is 82.188 grams. What I didn't show you was when I weighed the empty dish had a mass of 79.740 grams. So the mass of the sample is going to be the mass 82.188 minus 79.740. That'll give me the mass of the sample. So now what I'm going to do is I'm going to take the sample into the fume hood and begin to heat it up so that I can start subliming off the ammonium chloride. That step we have to do in the fume hood because the ammonium vapors is not something that we preferably would want to be breathing in. So we're going to do that in the fume hood so that it goes up through the exhaust system and not out into the lab. So I'll walk over to the fume hood, we'll get that sample set up, and then we're going to start to heat it up. Okay, so when I do the math for this and I take 82.188 and subtract 79.740, I get the answer 2.448, right? And so when we look at the significant figures and we want to see how many significant figures we should have in our answer, when we're doing subtraction, we need to look at how many numbers we have after the decimal point. And so in the first number, 79.740, I have 3 numbers after the decimal point. And this 0, since it's a trailing 0 after the decimal, right, I'll make that decimal point a little darker so you can see it. That trailing 0 after the decimal is considered significant. So the number 79.740 has a total of 5 significant figures, but it has 3 significant numbers after the decimal, which is the same as the number 82.188. That also has a total of 5 significant figures, but it has 3 significant figures after the decimal. So when I do subtraction, I want to match decimal places. So I want my answer to also have 3 decimal places. So 82.188 minus 79.740 gives me 2.448. That number has 4 significant figures in it, but the important thing is that I've got 3 decimal places, just the same as in my 2 original measurements. So it's 2.448 with 3 numbers after the decimal. Here's my setup inside of the fume hood, and I've got the sash closed here because I didn't want too much sound to be coming out so that it would be difficult to hear. But you can see I've got a ring stand. On top of the ring stand I have a Bunsen burner, and that's connected to the blue valve inside. So the gas is typically blue in the laboratories, air is orange, vacuum is yellow, and then water, cold water in this case, is green. So things are usually color coded. So the blue knobs are the ones that we use for the natural gas. And so I'm going to turn on the gas and go ahead and light the Bunsen burner, and then I'm going to take my dish, I'm going to separate that on that little clay triangle there so that the heat from the Bunsen burner is going to warm up my evaporating dish and get the ammonium chloride to sublime. So the first thing we do is we turn the gas all the way on, and usually the way that I found the simplest is to move the Bunsen burner out so that it's not right under the ring stand, because then otherwise it can be kind of hard to light it. So what I usually do is light it outside of the ring stand and then place it under the ring stand. And so now I've got my Bunsen burner there, and I'm ready to go ahead and place my evaporating dish on top of that. And so what should happen over time is that within a few minutes that ammonium chloride should start to sublime once the temperature gets to about 350 degrees Celsius. And I'm going to continue to allow that ammonium chloride to sublime off. It could take about 15 minutes until there is no more of it left. So again, I want to make sure that I'm getting all of it out. So I will let this go for a little while, and then when it starts nearing the end, I'll show you kind of what it looks like, and you'll be able to see some of the smoke subliming off of that. So I'll see you in a bit. So now my sample is starting to sublime off pretty well. You can see that white vapor coming up out of the dish, and that's the ammonium chloride going from the solid state right into the gaseous state. And so the important thing is that while that's occurring, that I need to keep stirring this, because I need to make sure that any of that ammonium chloride that might be in there, that it stays evenly mixed and that none of it's hiding, so that I can go ahead and make sure that all of it gets out. You'll also notice that on the tip of my stir rod, right, if I show you the tip of my stir rod, you can see that the tip of the stir rod is starting to get white, and so it's getting coated with solid ammonium chloride, that as that ammonium chloride is subliming off, it's condensing and then reforming as a solid on the tip of the stir rod. What's important for me is that I make sure that I don't get any of the other two compounds stuck on the end of the stir rod, that I could also be getting some of the sodium chloride, and I could also be getting some of the sand adhered to the tip of my stirring rod. So that could be a potential source of error down the road if my results are askew, that it might be that some of my samples stuck to the tip of the stir rod. So this is I'm gonna let this keep going for a little bit, and then when it's all done, we'll take it off of the heat, allow it to cool, and then we'll weigh it to get a final weight after heating. So, welcome back. I have now weighed my evaporating dish after I've allowed it to cool off. So this is after part one, where I've sublimed off the ammonium chloride. So if I come to my table, I can say that, okay, my mass of my sample, 2.448 grams, and now after heating, the mass of my dish and sample is 81.705 grams. So the mass of the ammonium chloride is going to be this value here, 82.188, mass of dish and the sample before heating, minus the mass of the dish and the sample after heating. That will give me the total mass of ammonium chloride that I lost. Then I'll take that number, the mass of the ammonium chloride, and divide it by the mass of the original sample. Multiply that by 100%, and that will give me a mass percentage of ammonium chloride in the original sample. And over here to the right gives you a place to kind of show your calculations. Once I'm done with that, I'm going to take this dish that has my sand and sodium chloride in it, and if I look at the next section, now I move on to part B, which is the extraction of the sodium chloride, NaCl. And in order to do that, in this step, right, I've got my sand in there, which does not dissolve in water, and I've got my sodium chloride, which does dissolve in water. So I'm going to go through a rinsing process. I'm going to add 20 to 25 mils of distilled water. Distilled water is water that has had all the minerals removed out of it, because I don't want to be adding any extra substances to it. I just want pure water. I'm going to add about 20 to 25 mils of water to that, stir it for about 5 minutes, and then obtain a second clean, dry evaporating dish, which I have right here. And after I've taken this sample, added the water to it, and stirred it up, all the salt is going to dissolve in the water. I'm going to pour that water into this second dish. Then I'm going to repeat that process a couple more times, adding more water, stirring, pouring off the water, adding more water, stirring, and then pouring off the water to try, because I want to make sure I get all of the salt out that I possibly can. So my second dish, if I go here now to part C, table 3, I've written down the mass of the empty dish number 2 and the mass of the dry watch glass. And so that's my empty dish and my dry watch glass. That's going to be the watch glass and the dish that have the salt in it. When I evaporate the salt off, I want to make sure I have the watch glass on top, because this sample tends to splatter as it's evaporating, as the water starts to boil, and I don't want any of the salt being lost from the container. I want to make sure it all stays in, so essentially the watch glass just acts as a lid to keep all the sample inside. So I'm going to go ahead and start that process of adding the water, pouring it off into the second dish, and then repeating that process a couple times. So on the report on the laboratory, I'm going to be working through part B of the lab, And then when I get to the end of that section, then I'll come back and explain that now I'm going to go through the process of drying the sand and drying the salt at the same time. So I'm at the point now where I have taken my sample that contained the salt and the sodium chloride, or the salt and the silicon dioxide, salt and sand, and I added water to the sand, rinsed it, poured it off, and I repeated that process 3 times, added a total of 45 milliliters of water. So now I have my first evaporating dish that has the wet sand in it. So I'm going to heat that up just to evaporate off the water and then end up finally with dry sand. And then I'll weigh that when that's all done, and we'll be able to calculate the mass of the dry sand that's left. Here is the dish that has the salt water that's been poured off of the sand. And so this now I'm going to evaporate, and I have a watch glass that I'm going to place on the top of that so that I don't get any splattering occurring in that process. So I'm going to turn on the gas and begin to heat this up so that I can start evaporating off all the water. So again, I lit my Bunsen burner over here, and then I'm going to place it underneath my evaporating dish, place the watch glass on top, right, and then kind of adjust the flame a little bit. So I don't want it too high. I want my sample to evaporate, but I don't want it to go too crazy too quickly. And so we'll let that evaporate. Right, we'll be able to see at some point, we'll be able to start seeing steam coming out of the opening there. You'll see some water condensing on the top of the watch glass or on the inside of the watch glass. You'll also probably see some salt starting to crystallize on the top of the watch glass. So we will let both of these samples evaporate. We have the salt water here. We're going to evaporate off all the water, and we're going to be left with dry salt. And then over here in this other evaporating dish, I have my wet sand, and I'm evaporating off the water from that, and I will be left with dry sand. You can see the progress that's being made. Here is my sand, which now looks a lot drier. You can see that it's a little more free-flowing, right? Wet sand kind of tends to clump together. Dry sand tends to flow a little easier. It's not sticking to the end of the glass stirring rod, so we know it's a little more dry. And then if I were to kind of grab the end of the dish, I'm trying to get my glove on here, and grab the end of the dish, and kind of, you can kind of see how it, right, the sand kind of flows a little easier, slides around in there. So those are kind of indications that it's not wet, it's not sticking together. So we'll give it a couple more minutes until it's completely dry. Here is my saltwater solution. So you can see the saltwater solution, the water is being evaporated off. You can see the water inside boiling nicely. You can see some droplets forming there on the top of the watch glass, and so probably when this is all done, that watch glass is going to kind of have a crusty layer of salt on the top, which again is why we weighed it beforehand, so when we're done we can just weigh this whole apparatus with the dish and the watch glass combined. The mass of the dry sand in the dish is 80.911 grams. So this is after I've allowed the dish to cool and weighed it. We don't want to put hot things into the balance to weigh them, because the hot, it can radiate heat, and that can lead to convection currents, and then that will change the weight, and the weight will actually start to fluctuate. It's fluctuating just a tad here, 80.910. But we can change our data then and write that value and say 80.91, right? This is why pencils come with erasers. This is why we do labs in pencils. There is the mass of our dish and dry sand. So subtract line 7 from line 8, and that'll give us the mass of the sand. The mass of our sample, which we had from line 3 on table 1, that should be the same, and then value the number 9 divided by the value here in line 10, multiplied by 100% will give us our percentage of sand. So we'll go check to see how our salt is doing. As you can see, here is our dish with the watch glass on it containing our dried salt. And so as I mentioned, you can see all the crusty salt that's kind of splattered onto the watch glass. And again, if we hadn't had the watch glass, that mass of salt would have been lost. When we look inside the dish, just a couple observations, you can kind of see that there's some coloring going on. Not sure what went on there, that maybe perhaps there was some contamination present either in the dish or in the sample, but you can see inside. I'll go ahead and remove the watch glass so that we can see a little better. Right, so there's our dried sand on the inside of the dish, and so we'll go ahead and we'll weigh that sample once it's cooled, and then we'll determine what the final mass of our sand was and figure out the percentages of all our samples. We now have the final weight of our dish with the watch glass and the dry salt, and that is 123.062 grams. So that's our final mass that we need. So 123.062 grams, right? And so now we have all the values that we need, and we can go ahead and finish up the rest of the lab. We can figure out what the mass of the sodium chloride is. We can figure out then what the mass of our sample, well, again, that's the same value from the previous page, right? We started out with 2.448 grams of sample, and we can figure out the mass percent. So the last part of the lab is the summary, and so in the summary what we're going to do is we're going to fill out table 4 here, and we're going to get the masses from the previous tables. So the mass of the ammonium chloride, that was from table 1, and what percent composition, what was the percent of the ammonium chloride in that sample. And then from table 2 we're going to get the mass of the dry sand, what its percent composition was. And then the same thing for the sodium chloride, its mass from table 3 and its percent composition from table 3. So the last little bit then is to do the final check and say, okay, well, what was the total, right? Because we had all these masses that we started with, and we should have hopefully accounted for all of them. So when we get here to the final end and we add up all our percent compositions, what should all those percent compositions add up to? Right, and so that's the question here. After you filled in that table, right, the questions, theoretically, what should be the total percentage? Right, well, you can think about that, and I'm not going to give you the exact answer, but what is your percent recovery, right? So when you add up your 3%, what do those values add up to? What does your mass that these add up to divided by the original sample times 100? Okay. The second question in the post-lab section says, could the separation in this experiment have been done in a different order? Well, the answer is not no, right? It says the answer is yes. You can't just write no and then move on to the next question. So I ask you to propose an alternative procedure. And so by meaning that, think about what we did in the very first step, right? In the very first step, what was it that we did? And could we have done something different in that first step, right? So if you think about the procedure, if you think about the order at which we did things, could we have done one of the other steps first instead, right? And how that might have changed our results. And then there's some questions, some last few questions here on the back. What is your most likely source of error? Well, see, this is one of the advantages to me doing the lab, right? Because anything that may have gone wrong as far as the procedure, well, that's on me. It's always good to work not alone in the lab. If you work with a lab partner, then you have somebody you can blame for your mistakes. But typically when we look at our sources of error, we're looking at the things that we measured, right? And what were the things that we measured, and what's the most likely measurement error that we may have done, right? And then some other questions as far as what could account for the ammonium chloride percent being too small. Well, that's hypothetically, right? When we do this lab, we know, or we will know when we're all done, what the actual percentages of the 3 compounds were in that original mixture. And so hypothetically, if we find out that our ammonium chloride was 20%, that's what our calculations told us, right? But according to the stockroom who made up the mixture, that it was actually 40%, right? Why did we get a smaller calculated value than what was actually there? Right, so again, think about what might have gone wrong, or what mistakes have been made that would account for us recovering too little bit of an ammonium chloride. And then the question says that if half of the ammonium chloride remained in the mixture after sublimation, right? So we didn't get, right, so we started out with so many grams of ammonium chloride in our sample, and not all of that got dissolved or sublimed out actually. What would happen to it as far as the rest of the experiment? How would this affect the percent composition values you calculated for SiO2 and sodium chloride? Right, well, the one thing I will tell you in relation to that question is that the ammonium chloride also dissolves in water. Okay, so think about what's going to happen to it if some of it remains in the dish, and we know that it also dissolves in water. Okay. So again, this lab, it's got the pre-lab section. Those questions you still need to answer. Read through the introduction, and once you read through that introduction, those questions, you'll be able to answer out the pre-lab. We're going to start talking about mixtures here in lecture in just a little bit, if we haven't already by the time you get to this. And then when you fill in your calculations and turn in the lab, and you can answer all those post-lab questions. All right, so I can be back for some final words, and I'll see you later. So that's it for the lab for today. Thanks for watching. Thanks for being a part of it. Wish you could have been here in person. I just want to let you know that if you have any questions about anything, you're more than welcome to ask. You can send me a message over Canvas, and I'll try and get back to you as soon as I can. So this lab will be due a week from the day that this video is posted, which should be the 14th of March. So it will be due on the 21st. Have a good rest of your day, and I'll talk to you later.